Hi folks, in this section we're going to talk about graphs of the other circular functions. So in the last section we talked about extending secant, cosecant, tangent, and cotangent to all angles via the definition of sine and cosine on the unit circle. So now we're going to look at these graphs. So it bears repeating how we get these other functions as functions of real numbers. We start off with the real number t, and then we go through the wrapping function, and we take the real number t and we identify it as an oriented arc on the unit circle, which matches it to an oriented angle in standard position, where the radian measure of that angle matches the value of the real number t. And then once we have that, we can define any of these trigonometric functions, any of these circular functions, I should say, more specifically, more generally circular functions, as a value of the angle theta. Okay, so there's sort of that composition happening here. So let's start with secant. Let's say we wanted to graph f of t equals secant of t. Well, as I mentioned in the last section, most folks find it easier to think about cosines than secants. And so we have that reciprocal identity that the secant of t is equal to 1 divided by the cosine of t. And so you might remember from college algebra straight away that we've got variables in the denominator, which means we have to worry about when that denominator is equal to 0. So in fact, cosine of t equals 0. If I think back to the unit circle again, cosine of t is going to be 0. Cosine, remember, is the x-coordinate. So it's going to happen at these points on the y-axis. Okay, so what angles correspond to that? Well, this would be pi over 2, and moreover, any angle that's pi units off of pi over 2. So pi over 2, 3 pi over 2, negative pi over 2, etc. So already we're going to get something different. We're going to get something new than what we had before when we graph sine and cosine, as we've got our domain issues here. The domain is going to be the set of all t, such that the cosine of t is not 0, which is going to be the set of all t, so that t is not pi over 2 plus pi k, where k is an integer. Okay. Now in the text we talk about extended interval notation towards the end of the section, which oftentimes we don't have time to get to. If you want to engage on that on your own, feel free, and we can talk about it during class or during office hours. Okay. But that's the first one thing. So we're going to have to see what happens. If you think back to college algebra, when you divide by a quantity that gets close to 0, a couple different things could happen. All right, so we're going to have to be cognizant of that. But let's go ahead and start with cosine. We can start with the graph of cosine, and then think about the graph, what the graph would look like if we try to take reciprocals of those values. So let's fire up Desmos here, and let's graph let's graph the fundamental cycle of cosine. So we'll call that C of t. So we're going to just restrict ourselves from 0 to 2 pi. All right, and there it is. There's our fundamental cycle of cosine. And I'm going to want to graph the reciprocal of that. So let's just think about what's going to happen, and then we'll have Desmos fill in the details here. But if we just think about what's going to happen here, I lost my connection with the tablet. So let's try this again. Okay. So let's think about what's going to happen here. So the cosine of 0 is 1, and if I take the reciprocal of 1, I'm going to get 1. So I'm going to have that point there. And let's think about what's happening as I move here to the pi over 2. So I know that pi over 2, the cosine is 0, and we know that that's going to be something that's not in the domain. So if I look at the secant of t, which is 1 over the cosine of t. And I look at what happens as we get closer to pi over 2 from the left. So as t comes into pi over 2 from the left, the numerator, well, that's gonna stay 1, but the denominator is going to become a smaller and smaller positive number. Okay, so the cosine is going to be smaller and smaller positive number. So when I take the reciprocal of that, that's going to be a very big positive number. And we think back to rational functions in college algebra, this is going to create what's called a vertical asymptote. So we're going to have a vertical asymptote should come in here at t equal pi over 2. And I'm taking the reciprocals of all these numbers, so it should shoot up like that. Now, on the other side of pi over 2, what's going to happen? I'm going to have the numerator is 1, but now these are going to become very quote-unquote small and negative. So once again, small here means small in absolute value, all right, but they'll have a negative attached to it, and that's going to propel things down to minus infinity. I'm going to relabel this vertical asymptote up here. We're going to have 1 over negative 1, which is negative 1. And then the same thing is going to happen over here when I get to 3 pi over 2. Same thing's going to happen. Okay. Now on the other side of 3 pi over 2, I'm back to this situation that I had here between 0 and pi over 2. Now I'm taking the reciprocal of very small positive numbers, so we'll be heading to infinity. And then when I finish up here at 2 pi, I'm going to be symmetric like that. Okay. So this is what one cycle of the secant function should look like. Now let's go ahead and see if we're right. And we are. Okay, so there we go. So that's one cycle. Now, because the cosine function is periodic of period 2 pi, and the secant is just taking the reciprocal of that, okay? Once again, what's that mean? That means that the cosine values repeat every 2 pi units, and it takes 2 pi units to repeat every cosine value. So the same thing's going to happen with secant because we're just taking the reciprocal of that. So if I wanted to get the entire secant function, I would just copy and paste that fundamental cycle end to end, and there's the entire graph of the secant function. Okay. Now you can actually go in there if you want and create a table of values given the known values of cosine. You can flip them over to get your secant, but there it is. You can kind of see the cosine wave in there. Okay. And what I like to recommend is, the secant and then also the cosecant. These graphs are going to inherit a lot of properties from sine and cosine. So I always recommend sketching the corresponding sine and cosine wave first, as far as getting the frequency and phase shift and things like that. One thing you'll notice about the secant function is not only does it have gaps in the domain, we have these vertical asymptotes here, it also has gaps in the range. Because we're taking the reciprocals of numbers that are between -1 and 1, the numbers we get out are going to be 1 or bigger or -1 or smaller. So we have sort of this gap in the range. We can do the same thing with the cosecant functions. You can see here the sine wave is dotted. As we come into 0 from the right, we're getting the numerator is 1, but the denominator are small positive values like the sine of pi over 6, the sine of pi over 12, etc. And we get the asymptotic behavior here at 0 pi and 2 pi. So here's the fundamental cycle of the cosecant function. Once again, we have this gap in the range. And there's the graph of the entire cosecant function. Okay, so here are some properties of the secant and cosecant functions. So the secant function is defined as long as the cosine isn't 0. So that's going to rule out all your pi over 2's. All right. The range is going to pick up everything except between -1 and 1. On its domain, the function is continuous and smooth. So if we ignore what's happening at the vertical asymptotes, everything's fine. Just like the cosine function had that even symmetry, so cosine was symmetric about the y-axis, the secant function will be symmetric about the y-axis. So that inherits that property. If you wanted sort of an argument for that, to show a function is even, remember, means that when you take the function value of the opposite input, you get the same output as before. So if I look at the secant, for instance, of the opposite of t, I can convert that to cosines. Cosine is an even function, so it's going to absorb that negative, and then we're right back to the secant. Okay, so that would be the proof of that. But we can observe that symmetry here. And as we mentioned, the secant function will have a period of 2 pi. Cosecant then works the same way, except here we have to throw out the whole number multiples of pi from its domain, because that's where the sine would be 0. It's got the same range, continuous and smooth on its domain. Because the sine function is odd, the cosecant function is odd, and so we observe that symmetry here across the origin. If you take the opposite input, you get the opposite output. So we have this reflection here through the origin. Has period 2 pi. And we have these conversion formulas. You can convert cosecants to secants and secants back to cosecants using the same conversion formulas we had for sine and cosine. So once again, if you wanted to kind of go through and prove this, the cosecant of t plus pi over 2 I could write that as 1 over the sine of t plus pi over 2. The sine of t plus pi over 2, that's the cosine of t, because once again, sine and cosine are just these phase shifts of each other. And 1 over the cosine of t, that gets you back to the secant of t. Okay, and the other ones prove the same way. So let's talk about how we would go about graphing. So we talked about graphing the sine and cosines in the last section. And so, we can use transformations. At least that's the first example, we used transformations, but then we kind of got into the notion of period and phase shift and all that stuff. So here's what I recommend. Let's look at number 1 here. First thing I recommend, number 1, let's write the trigonometric function first. So let's write this as a secant of 2t plus 1. And then I like to think about what I call it the corresponding cosine. So the corresponding cosine curve would be minus 2 cosine of 2t plus 1. So I'm going to sketch this out and then think about flipping the cosine values and what effect that's going to have for this graph. Okay, so let's think about this in terms of the cosine characteristics. So we can see here that our a is -2, our b is 1, our omega is 2, and our phi is 0. Okay, so that this means that our amplitude is going to be 2, but we're going to have a reflection. B is 1, that means that our vertical shift is going to be up 1. Omega is 2, tells us our period is 2 pi over 2 is going to be just pi. So this is running twice as fast as the regular cosine curve, and this means we have no phase shift. Okay, so let's go ahead and graph this cosine curve. So let's see how we can use the graph of the cosine curve to graph the secant curve. So we want to go graphing negative 2 cosine of 2t plus 1. So we had our phase shift is 0, our period is pi. So we can chop that up into the 4 quarter marks there. Pi over 2, pi over 4, and then 3 pi over 4. The baseline, y equals 1. The amplitude is 2, but we have that negative out front. So remember, for the standard cosine curve, we start high, middle, low, middle, high. So if we have a negative cosine t, that's going to invert it. We'll have low, middle, high, middle, low. All right. So we're going to start here low. How low is low? Well, we're going to go 2 units below the baseline. So if we start at y equals 1, our cosine curve would start down here at y equals negative 1. And then we would move to the baseline, the middle, pi over 4, would be up at 1. Pi over 2 would be the high point. That would be 2 units above the baseline, up here at 3. At 3 pi over 4, we'd be at the baseline, and at pi, we're back to negative 1. So we can connect these in the nice little wave-like fashion, and there's our cosine curve. So how can we use this to help us graph the secant curve? Well, we can do the same thing we did before when we got the secant curve from the cosine curve. We're going to be just inverting the cosine values. Okay, so once we determine the cosine value, we'd flip it over to get the secant value, but notice the arithmetic here for the rest of it's going to be the same. We'll be multiplying by negative 2 and adding 1. Now the key values we have here when we have secants, they're all going to be plus or minus 1. So for example, when I plug in t equals 0, the cosine of 0 is 1. When I flip 1 over, the secant of 0 is also 1. So 1 times negative 2 plus 1 is going to give me the same number whether I'm here or here. So this negative 1 is going to be the output from the secant function, just like it was the cosine function. Right? Now when I get to the middle here, the baseline, remember that corresponds to the zeros of the cosine function, and so that's where the secant is going to have an issue. So for example, when I plug in the pi over 4, 2 times the pi over 4 gives you pi over 2. This is where the cosine is 0. This is where the secant is going to produce a vertical asymptote. So I'll go ahead and dot in, or dash in rather, my vertical asymptote at t equal pi over 4. Moving along to pi over 2, the cosine of 2 times pi over 2, 2 times pi over 2 gets me pi. The cosine of pi is negative 1, and guess what? The reciprocal is also negative 1. So the same arithmetic I get here, negative 2 times negative 1 plus 1, is the same arithmetic I get here. And so that's going to give me a positive 3 as well. At 3 pi over 4, guess what? I'm back to a vertical asymptote because 2 times 3 pi over 4 is 3 pi over 2. And the cosine of 3 pi over 2 is 0, which means the secant's undefined. And last but not least, when I get to pi, the angle I'm looking at is 2 pi. The cosine of 2 pi is 1. When I flip that over, I also get 1. So the arithmetic here is the same. As far as now filling in the rest of the curve, I know the shape of the secant function. I have a gap. So I'm going to have a gap between negative 1 and 3. So that's going to force the vertical asymptotes to fill in this way. So as I come into pi over 4 from the left, we're going to negative infinity. As I come into pi over 4 from the right, I'll be going to positive infinity. As I come into 3 pi over 4 from the left, positive infinity. 3 pi over 4 from the right, negative infinity. Okay? And just for example, as we come into pi over 4 from the left, look at what's happening. The cosine values are getting close to 0, right? But 0 from the positive direction. So I have a reciprocal of a very small positive number times a negative plus 1, so that's going to produce that function heading off to negative infinity. Okay. So pretty much if you know how to graph the cosine function, you fill in the vertical asymptotes, and then you can just create the graph so that there's a gap in the range, and there's your secant function. Let's check this out on Desmos to make sure this all ties out. So we'll graph one cycle of that cosine function. There it is. Whoops. And it's even in blue for us. That's nice. And now for the secant function, we'll just we can copy and paste most of this here. Except we're going to just flip this from cosine to secant, and there we can see how it all fits together for you. Okay. All right, let's take a look at graphing g of t. So g of t here is cosecant of negative pi minus negative pi t minus pi minus 5 all over 3. So once again, we kind of want to look at the corresponding sine function. And we want to write that in that standard sinusoidal form. So when we went through and did the sinusoids back in section 10.3, this is sort of the standard form we had. So we need to do a little bit of algebra first before we can start the graphing. So you notice we have we're subtracting two terms divided by 3, so we can separate the numerators here. This is really just a distributive property here. Sine of minus pi t minus pi all over 3 minus 5 over 3. We can write this divided by 3 as a coefficient. And remember, when we worked these sinusoids, we always wanted omega to be positive. So we can see here we can factor a negative 1 out of both terms inside the sine function. So we look at factoring a negative out of the argument of the sine. That would give me a pi t plus pi. And since sine is an odd function, I can migrate that negative out front. Okay. Now we can actually simplify this even a little bit more if we had some identities, or if we think through some geometry here. But we're just going to leave it like this because that might not always be the case that we can simplify things. But this is possible to simplify this, to actually make this a 1/3 and get rid of the phase shift. But that might be something you can think about in the privacy of your own home. Okay, so we did some work here. And so once again, now we're going to graph y equals negative 1/3 sine of pi t plus pi minus 5/3. So this is what we're going to graph for our sine, and then we'll be able to get to the cosecant graph in short order. All right, so let's write down what we've got here. We can identify a here as minus 1/3. So it means our amplitude is going to be 1/3, but the curve is going to be flipped over. Our b here is minus 5/3, so that's going to be our baseline, will be minus 5/3. Omega here is pi, so our period is 2 pi over omega. That's 2 pi over pi, so the period is just 2. Our phase angle is also pi, so our phase shift minus phi over omega would be minus pi over pi, and that is going to be minus 1. So we're going to start here at minus 1. So let's go ahead and graph the corresponding sine wave that goes with this information. So we're going to start at -1. Got a period of 2, amplitude of 1/3, baseline of -5/3. Go ahead and graph here. Oops. We'll be looking mostly beneath the t-axis on this one, it looks like. And we'll graph this in blue. Okay, so we're going to start over here at -1. We got a period of 2, so we'll be finishing up here at 1. We put in the quarter marks here. So 0, -1/2, 1/2. The baseline here is -5/3. I'm just going to call it that. The amplitude is 1/3, but we're flipped over. So the standard sine function goes middle, high, middle, low, middle. If we want to invert that, negative then would be middle, low, middle, high, middle. All right, so this is what we're going to be starting at. I'm going to start at the middle. So -1, we're going to be down here at -5/3. Then we're going to go below. How far below? 1/3. So if I go down 1/3 from -5/3, I'm going to be at -6/3, which is at -2. Then I'll be back to the middle. Then I'm going to go high. So I go up, be at -4/3. That'd be up there. And then back to the middle there at 1. And once again, feel free to plug in values to check it. So if you're not too sure about what's going on here at 1/2, plug 1/2 in. When t is 1/2, I've got pi over 2 plus pi. That's 3 pi's over 2. The sine of 3 pi over 2 is -1 times -1/3 is +1/3 minus 5/3, -4/3. You follow? So that's what's nice about these, quarter marks, is these quarter marks correspond, if you've done the arithmetic correctly, to the quadrantal angles. So their values are, for sine and cosine, are either 0, 1, or -1. Okay. Now we're going to connect this in a pleasing fashion. All right. Let's do the cosecant curve now. So let's graph this, right? We'll do that in red. So once again, the values here at the baseline correspond to where the sine values are 0. So for example, when I plug in -1, I get the sine of -5 plus pi. That's a sine of 0. That's where the cosecant is going to have its issue. So anywhere we're at the baseline, just like with the secant curve, those values where we get to the baseline are going to be the values that produce the vertical asymptotes. So here they come, like so. And just like with graphing the secant, I know that I'm going to get these values here. And I'm going to create a gap in the range. So for that to happen, I'm going to need this portion of the graph heading off to -infinity, and then this portion of the graph heading off to +infinity. And so we can check to see that this tracks on Desmos. So let's change it up a little bit. We'll call it S of t for sine of t. We're going to go from -1 to 1. I went a little too far there. -1/3 sine of, pi t plus pi minus 5/3. So there it is. We can do a quick check there. -1/2, -2. 1/2, that's the decimal equivalent of -4/3. And then we've got 0 here, -5/3. And then for the cosecant, So that'll do it for example 1. Okay, so we can do with the secant and cosecant curves the same thing we did with the sine and cosine curves, and namely talk about these characteristics in general. So once again, these are represented in the same way we represented the cosine and sine curves. We assume omega is positive because of even odd properties, and all of these properties are inherited from the sine and cosine curves. So they'll have period 2 pi over omega, phase shift minus phi over omega, baseline b, and the a, you take the absolute value of a, that's how far the gap will be between the baseline and the lowest and highest point, or I should say, yeah, the local max and local min there on the graph. So example 2, here's a graph, come up with a secant and a cosecant function that could model that graph. So first let's start off looking at some of the characteristics we can see right away. If I wanted to figure out what the period is, remember that's going to be the length of this interval. So it goes from minus pi over 6 to 5 pi over 6. So that's a length of pi. And if that isn't, if you don't see that right away, just subtract the endpoints. You're going to get 6 pi over 6, which is pi. So the period here is pi. All right, so remember that means that 2 pi over omega is pi, and I can multiply pi omega is 2 pi, or omega is 2. So I've got omega is 2 now, so that's one characteristic I have right away. Phase shift is going to depend on if I'm doing secant or cosecant. Okay, but the omega equals 2, that's going to be the same for all of it. Now let's look for baseline and amplitude. Because the baseline, remember, is going to be the average, right? It's going to go right in the middle here. So if I look at, this appears to be right on the t-axis. So this looks like we've got a y-coordinate of 0 here. This looks like we've got a y-coordinate of negative 2 here. So if I look at the baseline, I'm going to take the average of those two, which you could probably guess, or probably see right away, it's going to be minus 1. And as far as my amplitude, well, I know that the absolute value of A is going to be the amplitude, and that's going to be the gap between the baseline and these points, so that's going to be 1. And once again, do we have a positive 1 or negative 1? That could depend on how we set all of this up, right? So these are the things that are going to be common to both the secant and the cosecant representations. So let's start working on the secant. So I'm just going to record this up here for posterity here. Okay, so let's work on the secant. So I know that the regular secant curve comes from the cosine. So cosine does this. When I flip cosine over, I get the vertical asymptotes at the baseline values. So the base secant function looks like this. So I have part of the graph, the asymptote, part of the graph, then the asymptote. So if I want to figure out like where the phase shift is on this one, I'm probably going to have to start it here at, I'll just say we'll start it at pi over 12. So we're going to start here at pi over 12 for looking at the secant. And so if I use the symmetry here, there'd be a point over here heading down that way. And so I'm going to look at this as being our basic here. So once again, I know the period is pi. So if I would add pi to pi over 12, this would be over here. I extend this here, that would be 13 pi's over 12. All right. Another 3 pi over 12 away from the 5 pi over 6. So this is what I'm looking at for my secant. And the first thing I notice is that it's inverted. So it's going to give us a negative. So let's start building this. Our A here would be a negative 1 because it's inverted. All right. So I got that now. And this also tells me my phase shift. So the phase shift in this formulation would be pi over 12. So minus phi over omega is pi over 12. So minus phi would be pi over 12 times omega. I know that omega is 2 because the period is only pi. That's pi over 6. This gives me that phi is minus pi over 6. So if I put all of this together, my capital F of t here, my secant version of this, would be A, which is negative 1, times the secant of omega 2t plus phi minus pi over 6 plus b minus 1. And we can check this in a couple different ways. We could plug in the points. So let's plug in, for example, over here we'll plug in the pi over 12. 2 times pi over 12 is pi over 6. Pi over 6 minus pi over 6 is 0. Secant of 0 is 1 times negative 1 minus 1. That gets us to negative 2. All right, let's plug in minus pi over 6. We should get something that's undefined. If I plug in minus pi over 6, I get negative 2 pi over 6 minus another pi over 6. That's a negative 3 pi over 6, which is negative pi over 2. Secant of negative pi over 2 is undefined because cosine of negative pi over 2 is 0. So that gives vertical asymptote. Okay, so we can check it that way. We could also fire up Desmos here and check it that way as well. So we'll put our f of t in here. And once again, we'll restrict things to what's in the picture there. We get minus secant of 2t minus pi over 6 minus 1. And there's the pi over 12 negative 2, 7 pi over 12 0. All right, so that's matching what we have there. Okay. All right. Now, what if we wanted to write this in the form of the cosecant? Okay, so what would be different and what would be the same? Well, what would be the same for the cosecant curve is our omega would still be 2, our baseline would still be minus 1. The absolute value of A, the amplitude, is still 1. But if I look at the traditional cosecant curve, to get that, we take the reciprocal of the sine value. So here's the typical sine graph, looks like this. And so when we go in to get the cosecant, right, once again at the baseline, we get these vertical asymptotes. And this is the behavior we get here for the cosecant function. So notice the orientation here is flipped. So as with the, if we're looking at negative pi over 6 as being the phase shift, we would have our A be negative 1 again. So our phase shift here, minus phi over omega, would be negative pi over 6. So minus phi would be minus pi over 6 times omega. But omega is 2, so that's negative, what, pi over 3. So phi would be a positive pi over 3. And now I can write this in terms of a cosecant curve. G of t would be minus 1 cosecant 2t plus pi over 3 minus 1. Okay, and that should give us what we see here. We can check that by plugging in values, or we can fire up Desmos here. So we are back at Desmos. Let's go ahead and type in our cosecant version of this graph. G of t equals, and I'm just going to copy and paste most of this here and just adjust. Instead of having secant now, we've converted it to cosecant. Instead of a minus pi over 6, we have a plus pi over 3. Boom. Okay. And you can see the graphs are indistinguishable. They match the original. Okay. Now, if you think back to section 10.3 when we had sinusoids, we could use those conversion formulas to convert sines to cosines by either adding or subtracting pi over 2. We can do the same kind of thing here. So if we go back, we have these conversion formulas that help us go from one to the next. So in particular, this one here, if I take secant of something, that's the same as cosecant of that same thing plus pi over 2. So if I start off with my f of t here as minus secant of 2t minus pi over 6 minus 1, I can convert this to cosecants minus cosecant of, and I can just think of this whole thing as being that theta. Okay, so I just have to add pi over 2 to that. So I'd have 2t minus pi over 6 plus pi over 2 minus 1. And by golly, look what happens if you add those together. If I have minus pi over 6 plus pi over 2, get yourself a common denominator of pi over 6's. You're going to get 2 pi over 6's, which guess what? That's your pi over 3. Which is exactly the formula we had for our g of t. Okay. Now, depending on how you set things up and what you use to start things and your phase shifts, you might not get the exact same numbers, but as you know, these functions are periodic, so you can add or subtract multiples of the period inside that function and still get the same graph. Okay, essentially they're the same function. All right, so I did want to point that out. So that'll do it for example. Okay, let's take a look at the graphs of the tangent and the cotangent functions. Now once again, going back to those quotient identities we had in the last section, we can think of tangent as being sine divided by cosine. So anytime cosine is 0, the tangent's going to have an issue. So the domains for the tangent and the secant functions are going to be the same. We have to throw out pi over 2 plus any whole number multiple of pi. Going through this similar kind of analysis as we get close to pi over 2, the sine of pi over 2 is getting close to, the sine of t is getting close to 1. The denominator is either getting close to 0 from the left or the right, so we either have very small positives or very small negatives. And when you go through, that's going to create vertical asymptotes here at pi over 2 and 3 pi over 2, just like they did with the secant graph. We can go in and plug some values, and we can plug more and more values, and this is what we would get if we plotted the tangent over the interval 0 to 2 pi. And if we would copy and paste it all the way down, we would get the graph of the tangent function. Something that we noted in the last section is because tangent is the ratio of sine over cosine. It's the ratio of the x and y coordinate in the unit circle. So when you take two positives and divide them, or two negatives and divide them, you get the same number. If one of those is positive, one of them is negative, you get the same number. So we get a period of pi because the ratio of plus to minus repeats. It doesn't take 4 quadrants to repeat that pattern when you divide them. Okay, it only takes 2 quadrants. So for that reason, we're going to take our fundamental cycle here for the tangent to be the negative pi over 2 to pi over 2. That's going to be the interval we focus on for tangent. Something we observe here certainly looks like tangent has symmetry about the origin. The graph, rather, has symmetry about the origin. Tangent is, in fact, an odd function. So once again, to be an odd function, it means that when you take the opposite input, you get the opposite output. And we can see that with tangent. If I plug in the opposite input and then take it back to sines and cosines, the odd property of sine says that the negative moves out. The even property of cosine means cosine absorbs the negative. So that's going to be minus sine t over cosine t, which sure enough is minus tangent t. So that actually proves tangent is an odd function. All right. We can do a similar kind of thing with cotangent. Cotangent is cosine over sine. So cotangent is going to have the same domain as the cosecant, because both of those functions will have issues when sine is 0. For example, as we come into, say, pi, the sine of pi is 0, the cosine of pi is -1. Depending on which direction you're approaching pi, you're either going to get -1 over a small negative or -1 over a small positive, which is going to produce your vertical asymptote. Copying and pasting together, once again, we see we've got a period of pi. Our fundamental cycle is going to be from 0 to pi. Right, we'll just pick that one. Okay. Cotangent is also odd for the same reason tangent is odd. If you just flip and put cosine over sine here, the negative pulls out of the sine but not the cosine, so cotangent is also odd. So let's put all these things together. Domains come from domains of secant and cosecant. We mentioned last time, or we mentioned in the last section as well, that the range of tangent and cotangent are actually all real numbers. So you get everything. There's no gaps in the ranges for them. They're continuous and smooth on their domains. Both functions are odd. They have period pi. And let's look at the conversion formulas. If we look at tangent and cotangent, let's fire up Desmos to graph both of these here. So we'll put t of t to be the tangent of t, and c of t to be the cotangent of t. They're off for more than just a phase shift, right? So if we try like the standard phase shift kind of a thing, like a pi over 2, they don't quite match up unless I put on a negative there to flip them over. Okay, so you can convert between tangents and cotangents, but along with the horizontal shift, there's also a reflection across the x-axis, and that's because we're flipping the fraction sine and cosine. Okay, so we do have conversion formulas. You can verify these from the conversion formulas for sine and cosine. Right? Okay, so let's graph one cycle of the following functions. Find the period. All right. So the way we approach tangent and cotangent is we got to think back to their fundamental cycles here. So if I look at the y equal tangent of t, its fundamental cycle is different. We don't start at 0 like we do the other 5 functions. We're going to start at negative pi over 2 and go to pi over 2. And when we chop it up into the quarter marks, same as before, we're going to have this shape. Got this increasing shape like that. Okay. So let's take a look at f of t, and let's rewrite it here. We'll put the tangent part first. Tangent of that t over 2, we're going to do that 1/2 t minus pi plus 1. So let's think about this. For the standard tangent, we're going to run between minus pi over 2 and pi over 2. So we're going to put this between minus pi over 2 and pi over 2, and we'll solve the inequality. The first step would be to add pi through the inequality. Now remember, pi is 2 pi's over 2. So you add up 2 pi's over 2 there would start at pi over 2. 2 pi's over 2 here give us 3 pi over 2. And last but not least, we can multiply through by 2. And this gives us our new fundamental, or where this fundamental cycle is going to live. So instead of between minus pi over 2 and pi over 2, we're going to be between pi and 3 pi. So we'll call this pi. We'll call this 3 pi. So that means that the period here, well, that's a length of 2 pi. So I'd have to chop this up into 4 equal pieces. All right, so we can find the midpoint here. We can add these together, divide by 2, 2 pi. Add these together and divide by 2, 3 pi over 2, and then another pi over 2 to the other side, 5 pi over 2. Okay, so that's our new fundamental cycle. And now we can plug these in and figure out what the graph is looking like. So if I plug in, say, a 3 pi over 2, 1/2 of 3 pi over 2 is 3 pi over 4. 3 pi over 4 minus pi would be 3 pi over 4 minus 4 pi over 4, so that'd be negative pi over 4. The tangent of negative pi over 4 is negative 1, times negative 1 is a positive 1, plus 1 is 2. So over here we're up at 2. I plug in the 2 pi. 1/2 of 2 pi is pi minus pi is 0. Tangent of 0 is 0. The opposite of 0 plus 1 is 1. So let's plug that 1 in there. Finally, 5 pi over 2. 1/2 of that is 5 pi over 4. Minus 4 pi over 4 gives you positive pi over 4. Tangent of pi over 4 is 1 times negative 1 plus 1. This gets us to 0. And so I connect it using that S shape here. Okay. So that'd be one cycle. Now the fact that we're decreasing now instead of the increasing, you can remember back to college algebra, that negative is going to flip it over. So instead of increasing, it will be decreasing. And we'll talk here in a minute about phase shift period and all that other good stuff. All right. Also, we have this vertical shift of +1. So there's a lot of stuff we're going to glean from this in general, like we did with the sine, cosine, secant, and cosecant curves. Right? But there we go. All right. We can check this on Desmos, as is our custom. F of t is 1 minus tangent of t over 2 minus pi. And we're graphing it from pi to 3 pi. Let's see if it'll pick up. Yeah, there's our 5 pi over 2, 0. We could check at 3 pi over 2 that we're at 2, and we could check at, what was the other one? Yeah, 3 pi over 2, and then we could check at 2 pi. Right, so there's our 2, 1, 0. 2, 1, 0. Okay? All right, let's take a look at that cotangent now. Cotangent of 2 pi minus pi t minus 1. So once again, we're going to rewrite things here. 2 cotangent of minus pi t plus 2 pi minus 1. And we'll factor out that negative using the odd property of cotangent. So we'll have 2 cotangent of. We'll factor the negative out from the terms in the argument here. Pi t minus 2 pi. And so negative 2 cotangent. Whoops. Pi t minus 2 pi minus 1. Right? Okay, now once again, we could actually simplify this a little further. We could have actually kind of done it up here as well. But you know, because of the period of tangent and cotangent being pi, we're subtracting a whole period off here. We can actually simplify this a little bit further, but just for now, we'll go through the usual sorts of machinations here. Looking at cotangent, our fundamental cycle of the cotangent here, we're picking between 0 and pi. So we're going to set this thing between 0 and pi. We can add 2 pi across and divide by pi. So this is going to be our new fundamental cycle, t between 2 and 3. We've got our vertical asymptotes there. We can divide this up into 4 pieces. So we take the midpoint here, it'd be 2.5. Oops. Which would be 5 halves. And then we divide that in 2. So that would be what? 2 1/4. So 8/4, 9/4, 10/4, and then 11/4, and then 12/4. So there's our quarter marks. Now we can plug these in. Plug in 9/4. 9 pi over 4 minus 8 pi over 4. Pi over 4. Cotangent of pi over 4 is 1. -2 minus 1 is -3. So we're down here at -3. Plug in 5 halves. Get 5 pi over 2 minus 2 pi. To be 5 pi over 2 minus 4 pi over 2, which is pi over 2. Cotangent pi over 2 is 0 times -2 minus 1. Now 11 pi over 4. 2 times 11 pi over 4 is 11 pi over 2 minus 4 pi over 2. Wait a minute, that's not right. Yeah, 11/4. Yeah, 11/4. 11 pi over 4 minus 2 pi would be 11 pi over 4 minus 8 pi over 4. Gives you 3 pi over 4. Cotangent of 3 pi over 4 is -1 times -2 is 2 minus 1 is 1. And connect them in that sort of S-shaped thing. And there you go. So once again, we have an increasing curve here. The standard cotangent is decreasing, but we're flipping it over. Let's fire up Desmos to check this one out. We've got our G of t. Two cotangent, 2 pi minus pi t minus 1, and we just looked from 2 to 3. There we go. We can check, spot check our values here. What do we have? We had 5 halves. Right. What do we have there? Whoops. 9/4 and 11/4. So 5 halves, we had -1. 9/4 and 11/4. All right, so that all tracks. Okay. I mentioned earlier about the concept of period. So just a little note here. The period of tangent and cotangent is pi. So as long as you have a even multiple of pi that you're adding or subtracting in here, the tangent's the same. So for example, like an f of t, we could totally rewrite this as 1 minus tangent of t over 2, because that's a multiple of the period of tangent. It's not going to affect anything. The same thing with g of t. That's a 2 pi. We could totally simplify that to minus pi t. Whoops. But since you can't simplify these things all the time, we want to just demonstrate the general method here. Because if you take generic functions, and you write them in this form, you knew this was coming, right? Your A, omega, your phi, and your B, we have the following properties. The period is going to be just pi over omega, right? Because the period of the standard tangent function is pi. So once again, the way you would get these formulas is you would say, okay, well, let's look. What's inside the tangent function here is omega. We can always rig omega to be positive using the odd properties of tangent and cotangent, and we would just basically sit omega t plus phi between minus pi over 2 and pi over 2. And then we would solve this. So if you're having deja vu, you should. This is exactly how we derived our formulas for sinusoids back in the day. Subtract phi, and then divide both sides by omega. Now when you divide by omega, that's the same as multiplying by 1 over omega. And since we're assuming omega is positive, we don't have to worry about fiddling with the inequalities at all. Okay. So if I wanted the period, I would just look at what the length of this interval is. And if you don't see it right away, we could always subtract the endpoints like we do. Look at what happens. We got a pi over 2 omega minus a negative pi over 2 omega. So those are going to add up. I've got a minus phi over omega minus a minus phi over omega. So these will actually drop out. So I get 2 pi over 2 omega, so there's our pi over omega. Another way to think about this, once again, think of transformations. The standard tangent has a period of pi. That's scaling omega times t. We're running omega times as fast as normal. So we take pi over omega, that's our period. As far as your phase shift goes, so it would be this one, okay? So you can think of that, if you wanted to, it's because we're starting here at negative pi over 2, so that's why that gets in the mix, okay? That's our phase shift. So that's how we get these properties, all right? We do have a baseline, a vertical shift here of y equals b. We don't really talk about a as an amplitude because these have infinite amplitudes and there's no gaps. So the only role that a is going to play, it will be the vertical stretch, and if a is positive, it'll keep tangent increasing. If a is negative, it'll keep tangent decreasing, and then the opposite for cotangent. The period for the cotangent would be the same, but the phase shift would be different, once again, because the standard cotangent cycle we have starting at 0 and running to pi, so when you subtract the phi divided by omega, we get that. Okay, so the phase shift for the cotangent is the same for the sine, cosine, secant, and cosecant, because all those start at 0. The one on tangent, once again, is just off by that pi over 2. Okay, let's take a look here at example 4. We're given the graph of a supposedly tangent and cotangent function, and we're asked to figure out what it could be. So let's start off with the properties that would be the same for both. Namely, let's go after the period. The period is how long it takes to complete one cycle. So we're running from -2 to 10. That's an interval of length 12. And if you need to double check that, we can just subtract the endpoints here. 10 minus -2. Sure enough, that's 12. That's going to help us figure out the angular frequency. So I know that pi over omega is going to have to be 12. Multiply both sides by omega. Divide both sides by 12. There's our angular frequency. Next, we can look at what the baseline should be. And unlike with sine and cosine, where we can average the max and min to get the baseline, or with secant and cosecant, where we can average the local max and local min to get the baseline, Here we just kind of have to trust that the middle point here, 4, 0, is that point of symmetry. That's the middle point for the tangent and cotangent. So we'll just take b to be 0. Now to go off and find the phi and the a, that's going to be specific to tangent and cotangent. So let's start working on tangent. So for the phase shift for tangent, instead of just being minus phi over omega, we have to account for that pi over 2. So this is the phase shift for tangent, and we're going to have this thing starting at -2. And I'm going to use the fact that my angular frequency here is pi over 12. So let's plug that in. And don't freak out right away. We'll handle the fraction gymnastics here in due course. When you divide by a fraction, you multiply by the reciprocal. So we can write the first term as minus 12 phi over pi, and the second term is minus 12 pi over 2 pi. But 12 pi over 2 pi is 6. Adding 6 to both sides, I get negative 12 phi over pi is positive 4. Multiplying by 4, dividing by negative 12. So I get my phase angle phi to be minus pi over 3. So at this point, my tangent function shaping up to be some value a tangent of pi over 12t minus pi over 3. And we still got to figure out what the a is. So at this point, we go back and look at the graph again. And we want to pick a point that's going to help us figure out what a is. So we don't want to plug in a -2 because that should give us undefined. I guess we could check that. But it looks like we've got the point 1, 3 on the graph. So we'll go back to the fundamental graphing idea. In order for 1, 3 to be on the graph, that means that when I plug in 1, I should get out 3. So let's plug in 1. A tangent of pi over 12 times 1 minus pi over 3. That should give us 3. If we go through here the arithmetic, pi over 12 minus pi over 3. We get a common denominator there. That's 4 pi's over 12. That's going to give me minus 3 pi's over 12, aka minus pi over 4, which is good because that's one of the standard quarter marks in the fundamental period for tangent. Tangent of minus pi over 4 is -1. So -1 times a, opposite of a is 3. So a equals -3. And we expected a to be negative because the curve is decreasing. So I put this all together in my tangent formula here. -3 tangent pi over 12t minus pi over 3. We can check this answer by plugging in the values on the graph, making sure they all tie out, or we could just fire up Desmos here. Let's do that. -3 tangent of here it is, it's already in here for us. So we can check here j of 1, j of 4, j of 7, right? So everything's where it's supposed to be. Okay. All right, how would we model this in terms of a cotangent? So for a cotangent, it's a little easier. We're still going to have our angular frequency be the same. We're still going to have our baseline be the same. But our phase shift is the same phase shift formula we've got for sine, cosine, secant, and cosecant. So minus phi over omega would be our -2 because the standard cotangent, the fundamental cycle we're taking for cotangent starts at 0. So I do the fraction gymnastics again. This is a little easier because I could actually just multiply both sides by pi over 12. And I get phi is positive pi over 6 once you go through the arithmetic there. So, I think we'll call it K of t. A cotangent of pi over 12t plus pi over 6 plus 0. And now I can play the same game I did before. I can use the fact that 1, 3 is on the graph to tell me that k of 1 has to be 3. So a times the cotangent of pi over 12 times 1 plus pi over 6 is equal to 3. What's pi over 12 plus pi over 6? Getting common denominators, pi over 12 plus 2 pi's over 6 gives me 3 pi's over 12, which is pi over 4. Once again, that's a good sign because that's one of the first quarter mark there in our fundamental cycle for cotangent. So a times the cotangent of pi over 4 is 3, but the cotangent of pi over 4 is positive 1. That gives us a is positive 3. So k of t is 3 cotangent pi over 12t plus pi over 6. And once again, we can check this using Desmos. So if we fire up Desmos here, we have a positive 3 cotangent of pi over 12 plus pi over 6. And sure enough, everything matches up. Okay. Once again, we could use the conversion formulas. Once we got a tangent or cotangent, we can convert to the other one using these conversion formulas. So if we look at, this formula here, for instance, if I rewrite this, this says that the tangent of something would be minus cotangent of that thing minus pi over 2. So another way we could get to this is if I look at my tangent was minus 3 tangent of pi over 12t minus pi over 3. So this would be, all right, so if I'm thinking of this whole thing here as my theta, I could subtract pi over 2 off of that and then make it negative. So making it negative would make that a 3 cotangent of, and I'd have pi over 12 minus t minus, pi over 12t minus pi over 3 minus pi over 2. If I get the common denominators here, that's pi over 6's. So we'd have 2 pi over 6's and 3 pi over 6's. So it'd be a minus 5 pi over 6. Okay, so we could get it that way. Now this looks different than what we had, right? So we ended up getting 3 cotangent of pi over 12t plus pi over 6, but hold on, let's check. And then we'll explain why here. So let's do this. Let's just copy this. Nope. Sometimes Desmos really just likes to push my buttons here. Okay. Let's call this k of t, just to be a little different. Let's do minus 5 pi over 6. And let's make it a different color. Boom. All right. So once again, the graphs are indistinguishable. They represent the same function. They look a little different, but let's remember something about the period of the cotangent function is pi. So the cotangent of something would be the same as the cotangent of that same thing plus pi. So if I think of this as my something, right? Whoops. Yep. Let's fix this here. So if I look at my argument here, if I think of this as that something, if I take this something plus pi, pi is 6 pi's over 6. So if I add 6 pi's over 6, I get back to this version of it there. Okay. So you can use these conversion formulas as well, like we had with sine and cosine. They may look different, but if you go through and apply the periodicity of them, you're going to get the same thing. So if nothing else, I hope you realize when you go through these, when you check your answers, a lot of times in the homework we'll say, well, here's one answer, here's another answer. It really depends on how you approached it, what you picked as your phase shift, and if you did any conversion or not. All right. The best way to check your answer is when in doubt, write it out. You can check on Desmos, and if you want to do a deeper dive, you've always got some of these identities to be working with. So that'll do it for example 4. Finish the section here, the example 5, with the application of where these other trig functions might be useful. Let theta be the angle of inclination from an observation point on the ground, 42 feet away from the launch site of a model rocket. Assuming the model rocket is launched directly upwards, and then we have a couple of scenarios. All right, so let's draw a little picture here. So we're going to start here. We're going to have the ground. We'll assume the ground is flat. We're going to be launching a model rocket vertically into the air. So we'll assume a right angle there. And theta is the angle of inclination from the ground to the rocket. And we are told we are 42 feet away from the base of the model rocket. So find a formula for f of theta, the distance from the rocket to the ground in feet. Okay, so the distance from the rocket to the ground in feet. So the rocket to the ground, this is what we want to call f of theta. All right, so we assume we got a little right triangle here. F of theta would be the opposite side. 42 would be the adjacent side. So it looks like I can do a little tangent here. I know that the tangent of theta would be f of theta over 42 feet. So f of theta would be 42 tangent of theta, and this would be measured in feet. Find and interpret f of pi over 3. So if I plug in pi over 3, I get 42 times the tangent of pi over 3. Tangent of pi over 3 is root 3. So 42 root 3 would be my output, which means that when the angle of inclination is 42 feet, when the angle of inclination is pi over 3 radians, the rocket is 42 root 3 feet off of the ground. So f of pi over 3 is 42 square root of 3. So when the angle of inclination theta is pi over 3, the rocket is 42 root 3 feet off of the ground. And even though they don't ask for a decimal representation for this, it might be curious. So we can fire up Desmos here and get a decimal representation, 42 square root 3. That's roughly what, 72, 73 feet? So roughly 72.75 feet. Okay. So it's heading up. Find a formula for g of theta, the distance from the rocket to the observation point. Okay, so we'll draw our picture again. Here's our observation point. Here's the ground. Here's the rocket. Whoops. And now we're looking for the distance. So we got a little triangle in there. Boom. So there's my theta. The distance from the observation point to the rocket. All right. This is what we're calling g of theta. So g of theta would be the hypotenuse. Now once again, I'm told that we're 42 feet. So here I'm looking for the hypotenuse and I know the adjacent side. All right. So I could use cosine for this, or we could use secant, because secant would get the hypotenuse in the numerator there. So I have that the secant of theta is the hypotenuse over the adjacent, g of theta over 42 feet. So g of theta would be 42 secant of theta, and that's measured in feet. Find and interpret g of pi over 3. So g of pi over 3 would be 42 times the secant of pi over 3. Secant of pi over 3 is 1 over the cosine of pi over 3, so that would be 2, which is 84. So this means when theta is pi over 3, the rocket is 84 feet from the observation point. Okay. Find and interpret the behavior of f of theta and g of theta as theta comes into pi over 2 from the left. Okay, so let's look here. Oops. So f of theta is 42 tangent of theta. G of theta is 42 secant of theta. Theta is coming into pi over 2 from the left. So we can remember here what's going on with tangent and secant. So at pi over 2, tangent's heading off to infinity, coming in from the left. Secant is doing the same thing, okay? Because remember, in both of these, tangent is sine over cosine. Secant is 1 over cosine. As we come into pi over 2 from the left, the numerator here is getting close to 1. The numerator here is already 1. Cosine becomes a very, very small positive number. So that that fraction becomes a very large positive number, blows up to infinity. Okay, so these are both going to positive infinity. Now, does that make sense? Well, let's think about it. Here's the observation point. We're 42 feet away, and the rocket is heading up. Okay, so the further up it goes, right, that's theta. So theta going to pi over 2 from the left, so this would be like our angle of observation. You follow our angle of inclination. And the closer that gets to pi over 2, right, the more vertical the rocket has become, which explains why those distances are heading off to infinity. All right. So there's a practical application of when you would use a tangent and a secant, and a practical application or observation of what would generate a vertical asymptote. Okay, so that'll do it there for section 10.5.